Hello, welcome to everyone. So, in this electrochemical sensor lecture series, in the in the previous lecture, we discussed the how to fabricate the successful fabrication of hollow copper sulfate, then followed by polypyrrole coated copper sulfate, and we confirm the formation mechanism as well as the found product is exactly match with the standard things. So in this direction, next the as formed this hollow structure copper sulfide and polypyrrole coated hybrid composite further utilized as a sensing material or used as a sensing platform for the electrocatalytic and electrochemical sensor application. How the as obtained the hollow material will be beneficial for the electrocatalytic property compared to other conventional method. So the main advantage of this preparation method is a highly unique. It is a new approach compared to the existing report over the preparation of hollow structure material. Yes, here we did not use followed a single step. All the reactor mixed into the hydrothermal setup. Finally, we will get a highly porous copper sulfate coated hollow sphere. Whereas in the reported report, they will follow minimum 2 to 3 steps, and also we will get and also they will get a low yield and possible to collapse the final product. So it is a significant advantage without using any toxic chemical or without using any expensive reagent. Simply we use the SiO2 and copper acetate and ammonia solution as a precursor and apply the thermal treatment under the hydrothermal. We achieved a highly uniform copper sulfate spheres. So what will happen? The obtained material has been coated over the classic carbon electrode surface. Classic carbon is broadly used as a working electrode because it is a good conducting and smooth surface. So it is broadly used for the working electrode for various applications, including in particularly electrochemical sensor, electrochemical supercapacitor, and electrocatalyst application because it has a high stability. For example, this is the modified electrode with the different modification. Here we can see the four kind of cyclic voltammetry curve. We have measured the cyclic voltammetry curve in the potential between -0.2 to around 0.7 volt. So here curve A, this one green color curve C and red color curve B, and D is a curve D. So this is the different modified electrode. For example, electrode A means without any modification, which is called a bare electrode. Curve B means only copper sulfate at SiO2 modified electrode. And then this is only PPY modified electrode. This one, it is used for only the copper sulfide PPY coated hybrid composite modified electrode. These are the different modified electrode, and then we are adding here methanol in particular concentration. So see here the curve A, we have to compare the curve and A, B and C and D. See here the curve is a modified electrode of copper sulfide SiO2 over the classic carbon electrode before adding methanol. So after adding a particular concentration, I think 0.1 mole of methanol from this curve without addition of methanol, after adding methanol, the copper sulfide hollow structural electrode, we can see a strong oxidation peak. So whereas this curve C for the polypyrrole copper sulfate hybrid hollow structure modified electrode. Before adding methanol, we can see the very less current. After adding the methanol, the oxidation current has highly rapid. We have achieved a high current around in the current range of around 50 milliampere per centimeter squared. This is the insert so the corresponding oxidation current value for both the copper sulfide electrode and copper sulfide PPY hollow structure coated classic carbon electrode. If we use only copper sulfide, we are achieving nearly 20 milliampere per centimeter square. Whereas after coating of thin film of polypyrrole, it is nearly threefold increase the oxidation current or 2.5-fold increase the oxidation current because of what is the main reason for this much 2.5-fold increase oxidation current after coating a polypropylene when compared to the alone copper sulfate hollow sphere, because the polypropylene has a act as a membrane or act as a protecting layer for leaching the copper sulfide, for avoiding leaching the copper sulfide during the electrooxidation of methanol, because we are running this whole electrochemical setup in alkaline condition. It is known the metal in alkaline condition may possible to form a either corresponding hydroxide or it may leach slowly into the solution. So avoid this one, polypropylene act as a protecting layer, and also it has a small pore. It is easily penetrate into the methanol through the pore structure and assess the active site of the copper. So they enhance the oxidation current we have noticed or we have observed over the polypropylene coated copper sulfate hollow structure. Further, the main advantage of copper sulfate, the oxidation reaction, when generating the methanol oxidation, it produces electron. The electron effectively communicated through polypropylene coated copper sulfate through transducer electrode surface to the circuit. We will get a without any loss of oxidation peak current or electron, we will get a full oxidation output. Whereas in the only copper sulfate, some part of the things cannot fully transfer to the transducer, so we will get a limited current. Whereas polypropylene coated, it is a high conducting polypropylene, because the main advantage in the previous lecture we discussed the polypropylene unique property of the polypropylene. It has been active in both alkaline and neutral and also acidic medium. So this is the main advantage. Here, even if you are using the alkaline condition, the polypropylene has a highly electroactive and it can effectively communicate the electrooxidation reaction into the transducer surface. Hence, we observe without any loss of electrochemical catalytic performance and transfer effectively 100% through the transducer surface. Hence, we obtain a highly oxidizing or electrocatalytic property over the polypropylene coated copper sulfate hollow structure. Further, this high performance electrode we have used for the detailed study. Because some electrode material, what will happen when using a one, it will obey only particular state. After a different state, it may be the oxidation reaction mechanism may affect, or it cannot be does not oxidize, or the oxidation reaction will be reduced. In order to control or in order to verify the catalytic performance of the as fabricated polypropylene coated copper sulfate hollow sphere, we have performed a different scan rate from 10 to up to 100 millivolt. So what will happen when increasing the scan rate significantly, the oxidation peak current also gradually increasing. So which indicate that copper sulfate coated classic carbon electrode has high electrocatalytic characteristic towards the electrooxidation of methanol in extreme condition from low to high scan rate without any deviation of oxidation peak or without any suppression of oxidation peak current, because only the high performance catalyst can provide this characteristics oxidation peak. Suppose if the material has a low catalytic performance, what will happen? It may give a 10 at the 10 millivolt particular current density. When increasing, it may decrease the current density because the catalytic performance of the material may poor. So whereas in the case polypropylene coated copper sulfate hybrid composite modified classic carbon electrode exhibited a excellent catalytic performance. Hence, we achieved we have achieved a significant increment in the oxidation peak current with respect to the scan rate. So further, the concentration effect is another important parameter, because when developing any catalyst, it should be worked from a wide range of concentration from low to high. Hence, we have used the same cyclic voltammetry measurement to confirm whether the concentration increasing the catalytic performance has any affected over our fabricated catalyst. So initially the PPY copper sulfide hybrid electrode modified classic carbon electrode we have recorded a CV without any addition of methanol. After that we are adding sequential methanol addition, for example 0.1 mole, 0.2, 0.3, 0.4 and 0.5 molar methanol in 0.1 mole NaH solutions. Here we can clearly observe the when increasing the concentration, the oxidation peak current of the methanol at PPY copper sulfide hybrid material modified electrode significantly increase, further confirming the good catalytic characteristic of the our fabricated copper sulfide polypyrrole hybrid electrodes. So here it may be noted when plotting the scan rate, square root of scan rate versus oxidation peak current, we observed a perfect linearity between the oxidation peak current against square root of scan rate, because we applied a scan rate from 10 to 100 millivolt. So it indicate the square root of scan rate and current linear plot indicating the oxidation reaction of methanol at copper sulfide SaO2 modified electrode is a diffusion control process. The reaction is a actors are performing a diffusion control process rather than a surface control process. So here also in plotting the oxidation current of methanol and concentration, we obtain a good linearity. It confirms the fabricated electrode has a good catalytic characteristic towards the electrooxidation of methanol. So further stability is a main role or important for the developed any catalyst next level to bring the real usage or real application. Hence we have fabricated this electrocatalyst up to 10,000 seconds or hours. I think it may be some typical error. So here we performed this dark color line only for the copper sulfide modified classic carbon electrode, whereas red color indicate the polypyrrole copper sulfide hybrid composite modified electrode. So here we can observe different characteristics. One is the copper sulfide has a low current in the amperometric measurement. The stability was carried out by amperometric measurement. So the copper sulfide alone coated electrode, it exhibited only a low current, whereas PPY coated copper sulfide exhibited a high current. As this characteristic result we have noticed in the initial cyclic voltammetry also. Further, the stability also significantly reduced when increasing the time of the electrocatalytic reaction. It is due to the copper sulfate directly interact with methanol and electrolyte. Hence, the reaction may be the byproduct may affect the copper sulfide modified surface. So performance slowly decreases. Whereas in the polypyrrole coated, it has a nearly similar stability. The loss is very less compared to the alone copper sulfate. So the copper sulfate coated electrode delivered a high stability compared to alone copper sulfate coated modified classic carbon electrode. This phenomena, this improved oxidation peak current and good stability, mainly due to the coating of conducting polymer over the copper sulfate. So as explained previously, the polypyrrole behavior two role. One is it is act as a protecting the layer, so does not leach out the any copper ion or avoid the intermediate absorb over the during the methanol oxidation. It produces some intermediate, then intermediate easily absorb the catalytic active site and block the active site sites. Hence the catalytic performance slowly decrease. Whereas in this case of polypyrrole coated, it behavior some product the layer, so the copper sulfate does not affect by the oxidation product. Hence it continuously act as a or deliver a full catalytic performance up to long-term stability. Further, the copper sulfate has a good conductivity. Hence, it can be able to absorb a more number of or allow a more number of methanol molecule to interact with the copper sulfate active sites. The third advantage is copper sulfate is high conductivity property of this polymer, conducting polymer. The oxidation reaction generating an electron efficiently transfer through the transducer surface. So without losing any electron, it can be obtained a good properties. So another the same copper sulfide microflower structure has been prepared in the similar condition. So here we are using without any template we used for the preparation of achieving a copper sulfide microflower. The obtained copper sulfide microflower has a good catalytic property, energy storage property, and sensor property. So interestingly, the obtained copper sulfide copper sulfide microflower structure has been successfully utilized for the electrochemical glucose sensor application and energy storage application and oxidation electrocatalyst methanol oxidation application, because these three applications due to the peculiar property and highly catalytic of the site of copper sulfide. So compared to previous synthesis, here the synthesis is little we have changed. I will explain the following slide. So in previous slide, what will happen? We have used SiO2 as a hard template to prepare the hollow structure. Here, we did not use any template method. So just we have taken as a copper acetate as a copper precursor and sulfur powder used as a sulfur precursor. We mixed the ethanol as a solvent. In the previous reaction, we used a water as used as a solvent, but here we used as a ethanol. So here we can say this reaction is a solvothermal reaction because we used only solvent. We did not use any water or something. So we can call this a solvothermal reaction. Compared to previous reaction, here we avoid the SiO2 template and we change the solvent. Instead of water, here we are using ethanol. The remaining, the temperature slight changes. For example, in previous reaction we used 180, here 160. So I will explain the how, what are the things we are following to fabricate the copper sulfate microflower structure with the uniform morphology. Initially, we used the copper acetate as a copper precursor and sulfur powder used as a sulfur precursor mixed in these two powder in the ethanol solution. Followed by we are adding a certain amount of aqueous ammonia solutions. So the whole clear transparent solution were transferred into Teflon and kept into the autoclave setup with highly sealed and kept in a oven and the temperature was maintaining at 180 degree, sorry 160 degree for 16 hours. Followed by the whole setup was given or allowed to cool naturally into room temperature. Then it was opened. We obtained a black color powder which was collected by a centrifugation or through membrane filtration process and then washed with excess unreactant and byproduct from the formed black color powder. So finally we achieved only pure copper sulfate powder in the form of black color. So followed by the obtained copper sulfate has been used for the various electrochemical application. This is the simple electrochemical setup. What are the things we are using? The electrochemical experiment, including we used cyclic voltammetry. It is a common technique for we have used for electrochemical sensor and energy storage or electrocatalyst application. This is a preliminary study for cyclic voltammetry. And then galvanostatic sensor. It is mainly used for the energy storage application. And then electrochemical impedance spectroscopy. It is one of the powerful technique to verify the or to monitor the charge transfer resistance of the any modified electrode between the electrode and the electrolyte interface, and then chronoamperometry. So using the electrochemical workstation composed of modified, the copper sulfide modified electrode, classic carbon electrode, or nickel foam for supercapacitor used as a working electrode, and silver sulfide used as a reference electrode, and the platinum wire as a auxiliary electrode or counter electrode. We can call it as a auxiliary or counter electrode. This is the electrochemical setup for the prepared material has been studied. So before going to see the electrocatalytic or electrochemical sensor performance, we have to see the how the morphology product is formed, whether it is the product is perfectly matched with the standard So for the detailed characterization, we have verified with the different characterization. We will see the following slide. So see here, this is the epistem morphology. The A and B in the pink color image shows the epistem morphology of the as fabricated copper sulfide hollow sphere. Sorry, copper sulfide microflower structure. See here, we cannot see the any unwanted morphology or some residue morphology in the same image. We can see the uniform flower-like morphology over entire the same images. So this is the highly magnification image. We are focusing only the one microflower structure. We can see the highly flower-like morphology. Interestingly, the flower-like morphology composed of several thin nanoseeds. See here, if we in the high magnification image, we can see the thin layer of nanoseed assembled together to form the flower-like morphology. The thickness of the thin layer morphology we have estimated around 15 to 20 nanometer. Overall, the cross section of the morphology was estimated is to around 2 to 2.5 micrometer. Similarly, the FSM EDS mapping image further verified what are the elemental exist in the asparmed microflower, copper sulfide microflower section was confirmed by FSM mapping. This is the FSM mapping studies. This is FSM mapping studies. Here we can see clearly the formed microflower structure containing only the two elements. One is copper and is sulfur. We cannot see the any other or impurity or unwanted element. So the asparmed product contain only the copper and sulfur. And also it may be noted here throughout the flower morphology, uniform dispersion of copper. Here also, throughout the flower-like morphology, uniform distribution of sulfur, which indicate the asparmed microflower structure containing both copper and sulfur only, with high tense and uniform distribution of these two elements. So the simple reaction is for the formation of this copper sulfide morphology, we did not use any template, either hard template or surfactant or polymeric material. We did not apply to achieve this process. We simply use copper copper precursor and sulfur powder is a sulfur precursor in ethanol. So all are green approach. And also we apply a moderate temperature to achieve this product. So the hydrothermal process is a highly uniform synthesis of this copper sulfide microflower is a beneficial. So the same we have conducted in the literature. So they are already several report they have reported for the formation of copper sulfide hierarchical porous structure or microflower lecture, but mostly they achieved in presence of some special reagent or expensive or toxic reagent or template. So without using this reagent, no one achieved to obtain a uniform morphology. Even some reported they use some soft template to achieve this microflower, but they cannot achieve a highly uniform structure. Here we are achieved a highly uniform structure without aid of any surfactant or template. Followed by this obtain the morphology, the interior property was confirmed by the HRTM image. This is the flower. We can see that it is as a flower-like morphology. The average estimation of size here around 4.3. Sorry, here I explained 2.5. It is the cross-section size around 4.3 micrometer. So overall, this cross-section of the micro structure is here around 4 to 5 micrometer size. Uniform size we have obtained. So whereas the assembled microflower composed of thin nanoseed. So it forms several thin nanoseed and make to form a finally it is a flower-like morphology. So the thickness of the nanoseed we estimated 15 to 20 nanometer. For the HRTM, we can verify the crystallinity of the property. So it is observed the copper sulfide has a high crystallinity nature. So see here it is a we formed a good crystal-like morphology. The clear SAD pattern, the bright dot indicate the asparmed copper sulfide has a good crystallinity, and it has a strong XRD peaks. We confirm so the obtained T spacing value are perfectly match with our obtained XRD result. So from this SEM and TEM and HR TEM study clearly confirm the successful formation of copper sulfate without any impurity or without any. Further, the crystal structure was confirmed by the XRD. This is the XRD spectra. So we have to achieve, because we used 116 hour and 160 degree. So we have to confirm the temperature as well as time. So in order to confirm, we have verified the different had the same hydrothermal reaction and a similar condition, we are following a different time interval, and then the collector product verified by FBSM, similarly different temperature. So from 1 hour to we have performed 12 hours. See here, when increasing the time 1 hour, 3 hours, 6 hours and 12 hours. When 1 hour, the morphology, irregular morphology, or it is like a spherical morphology has been observed. When increasing time, the spherical morphology slowly spread or slowly develop into some sheet-like morphology. Followed by, when increasing the further time up to 12 hours, we are getting the highly flower-like morphology. So it indicates the minimum 15 hours, 16 hours are required to achieve a highly uniform flower-like morphology. When increasing the further time, the morphology does not change. So we have optimized 16 hours is a controlled time or a sufficient time to form a well-defined flower-like morphology. Followed by, we have varied a different time. So initially we used 90 degree. So does not form any clear morphology, irregular particle morphology like observed. So it indicates that this 90 degree low temperature is not sufficient to form the perfect copper sulfide with the crystal structure. Followed by, when increasing 100 degree also, it is not any significant morphology. When increasing more than 100 like 120, we can see that some layered sheet like morphology. Further increasing 150, also 70 percentage flow like morphology can observe, but still is not clear. So further increasing the temperature 160 degree, we can get a full developed flower like morphology. When increasing further more than 160 like 180, the morphology does not change. It is similar to the 160 morphology. Hence, we have limited for successful formation of copper sulfate, we need a 16-hour reaction time, and 160 degree is sufficient to obtain a highly uniform copper sulfate microflower structures. So further, the XRD were investigated for prepare all the sample, all the optimized condition from 1 hour to 16 hour. And then this is the 1 hour to see here, the less time 1 hour, we cannot see all the peaks are very broad. When increasing the time, the crystallinity of the peak was gradually increasing up to 12 hours. After that, there is no much changes, but all the peaks are similar pattern and does not give any impurities peak. Similarly, when increasing the temperature, see 90 degree, we can see very broad peak compared to in this lower region from the 25 to 35 degree. So it indicates that the reaction does not complete, hence we are obtaining a very low broad peak. So further increasing the temperature from 120, slowly the peaks are getting very strong, and we get a highly intense peak and the temperature of more than 140 degree. So from this XRD we can clearly confirm the time and temperature are playing a important role to achieve a highly uniform copper sulfate flower-like morphology. So apart from the main advantage for the synthesis, it is a simple and green approach, does not involve any toxic chemical. Just we used only a copper precursor sulfur powder in ethanol. We did not use any toxic organic solvent or toxic chemical or expensive some surfactant or polymeric material. We simply achieve this highly uniform morphology, this flower-like morphology. It is composed of several thin layer of nanoseed. So further we will study the how this flower-like morphology will deliver a good catalytic performance or catalytic performance for the electrocatalytic application and the electrochemical glucose sensor oxidation application, and finally we discussed the energy storage application. Because of this different type of property it may give due to the unique property of this or unique characteristic of this copper sulfide microfluidic structure, because it has a special advantage compared to the other morphology. So thank you all. So next lecture series we will see the application of this copper sulfide morphologies.